So let's start. Hello everybody, and today we start next section, that is section 4 or 5. 4. Section 4, implicit function theorems. So let me start with explanations. We want to solve equations, and let's consider such a simple equation. And we want to solve it, let's say, with respect to the variable y. So, of course, we know how to solve it. Y equals to plus or minus square root of 1 minus x squared. And as you see, in general, we have two solutions for every x between minus 1 and 1. It means that this equation does not define one function, but in general it defines two functions. So the equation determines two functions. For x in minus 1, 1. And that is to say that the equation f of x y equals to 0, where f of x y equals to x squared plus y squared minus 1, determines the implicit function functions. In fact, two functions appear here, as you see. And here, in this situation, we can find those functions explicitly. But in general, if we have such an equation, then when we can do it, if it's difficult to solve it explicitly. So let me draw the graph and try to clarify in more details the meaning of this sentence. The equation determines two functions. So here is the graph of our equation, right? Now, how we can choose between those two functions? So, for example, if we fix a point x0, then in general we can find two possible values of y which satisfy that equation for x equals to x0. So x equals to x0, hence y equals to plus or minus square root of 1 minus x0 squared. But what is important? If we choose one of them, let's say here, right, then for arbitrary sufficiently small epsilon, so if that is y naught minus epsilon, and here y naught plus epsilon, we can find delta, again sufficiently small, such that for all x's here we can define uniquely a function such that inside this rectangle, so we have delta here, in fact 2 delta of course, 2 epsilon here, and we have rectangle. And what is property of this rectangle? Once x is in our interval near x naught, the equation x squared plus y squared equals to 1 and y equals to square root of 1 minus x squared, those equations are equivalent for x in that interval and y in y naught minus epsilon, y naught plus epsilon. So inside this rectangle, there is only one possibility to solve the equation x squared plus y squared equals to 1. And it happens for arbitrary x between -1 and 1, for arbitrary x naught. Sorry. So once we choose x naught between -1 and 1, we can, for arbitrary y naught, doesn't matter plus or minus, if we choose one of them, then we can solve the equation in such a rectangle uniquely. But there are exclusions. And one exclusion is here. So if x naught equals to 1, then it's impossible. So it doesn't matter how small epsilon we choose. In such a rectangle, you cannot solve the equation x squared plus y squared equals to 1 uniquely. It's impossible because you need to take both plus and minus values here, right? It's impossible. And in fact, the reason is very simple, because if we write it like that, then so we want to solve with respect to y, and if we compute partial derivative of f with respect to y, then it is equal to 2y, right? So for that point, y equals to 0, hence partial derivative equals to 0, and that is the reason why we cannot solve the equation. So of course that is a very elementary example when you solve explicitly everything, but the phenomenon is very general in fact. So you see, if partial derivative is not 0, then you can solve. If it is 0, in general you cannot. Of course, there are also exclusions when still you can solve, but that's another story. Okay, so now I can formulate the theorem. So theorem 1, which is just implicit function theorem. And I'll give it for more general situations than here. So here we have just 2 variables. Now I want to consider more general case. So Suppose f to be, let me write it here, f of x, y to be a differentiable function of n+1 variables in a neighborhood u of x naught y naught of a point of the point x naught y naught, and let me write it in coordinates also. Oh, usually we wrote like that. Right. Such that partial derivative of capital F with respect to y is continuous. In that neighborhood. If f at the point is equal to 0, so it's like here, and partial derivative of f with respect to y at the same point is not equal to 0, then for arbitrary epsilon greater than 0, there exists delta greater than 0 such that for every, not for every, such that there exists, too much of there exists, such that there exists, too many there exists. For all x in the cube, let me denote it by that, and that is product k from 1 up to n x k naught minus delta x k naught plus delta. It is possible to define uniquely a function y equals to, let's say, f of x such that the equations f of x y equals to 0 and y equals to f of x are equivalent in the Cartesian product of our cube times this interval. Moreover, f is differentiable in k delta x naught, and partial derivatives can be computed with respect to kth variable at x can be computed by the following rule. This is minus partial derivative of f with respect to xk at x f of x divided by partial derivative of f with respect to y at x f of x. That is how we can compute, here k varies from 1 up to n. So, of course, it seems rather huge, but what is? No capoeira over y. No. Y is one variable. So you see n plus 1 variables. X has n components, y just 1. So we solve the equation with respect to one variable. So like here we had two variables, but instead of 1x we could consider several variables like x, let's say, right? And in fourth line, oh, sorry, that is mistake. Thank you. That is mistake, misprint. Thank you. Okay. Yeah. Now proof. I'll proceed in general case, but I'll use to illustrate the proof the picture for two variables. So here is, let's say, firstly, let's imagine that is our neighborhood, and then, so roughly speaking, here we have x variable. That is not an axis. Of course, that is not the origin. That is the point x naught, but that is a parallel, right? So let's say x naught plus x, right? And here we have y naught plus y. Roughly speaking, imagine that n variables like one variable and y is second variable. Now, I said that firstly we imagine that this is our original neighborhood. And then I'll start to diminish it. The first reason to do it is to compare those two conditions. Look. First of all, without loss of generality, suppose partial derivative of f with respect to y is positive. Just to fix, right? Because it doesn't matter, positive or negative. Then this partial derivative also is positive in a neighborhood. Neighborhood of x not y not. So once again, that is a point x naught plus y naught. It's here, right? And we consider smaller neighborhood to be sure that this partial derivative is positive everywhere. Why we can do it? Because of continuity. So if this function is continuous and positive, then near that point is also positive. Near, so that is what we choose to be our neighborhood. Okay. Now, in fact, you see, here it is written for arbitrary epsilon greater than 0. So I should find for arbitrary epsilon such delta that for this rectangle we have something, right? And of course I can consider only sufficiently small epsilon, because if epsilon is large and I can find the solution in a smaller, with smaller epsilon, right? Then of course we found the solution in larger, because if we are smaller rectangle, then we are also simultaneously in larger rectangle, right? So it means that I can suppose that this arbitrary epsilon is sufficiently small, right? So consider arbitrary sufficiently small epsilon greater than 0 such that this interval, okay, let me take it together with the ends. Such that, okay, x naught times this belongs to that neighborhood. Maybe let me denote it in a neighborhood. Let it be capital B of our point, right, to B. And so that is precisely our B, right? That is precisely our B. So, look, that is our y naught plus epsilon here, right? Y naught minus epsilon. That is what we choose. Then, the function capital F at x naught y is differentiable on y naught minus epsilon, y naught plus epsilon with positive derivative. Why? Because look, I fix one variable, right? Oh, not one. First n variables, right? They are fixed. Only one variable varies. And if we differentiate that function, then that is precisely partial derivative with respect to y, right? And as we supposed, this partial derivative exists and it is positive, right? So we have function of one variable which is positive, right? Which increases, right? Strictly increases. Hence, it is increasing on y naught minus epsilon, y naught plus epsilon, and capital F x naught y naught equals to 0 by our supposition, right? 0. So, what it means, if it's increasing and the value at the middle point is 0, then what we have? If we substitute the left end, then that is negative, right? And the value at the right, and it's positive, right? So, here our function is positive and there is negative, right? Now we change roles. So, look. Firstly, what we did? We fixed first n variables and vary only the last one, right? Now, we fix the last variable and we'll start to vary all others. So, but we know the function capital F is differentiable, right? Hence it is continuous. So, f is continuous, f of x y naught plus epsilon and f of x y naught minus epsilon are continuous. Of course, in a neighborhood, right? In a neighborhood of x naught. Hence, they exist delta positive such that k delta x naught times our interval y naught minus epsilon, y naught plus epsilon is inside B, and for all x in our neighborhood, we have f of x y naught plus epsilon is positive, and f of x y naught minus epsilon is negative. So what we do, look, so our function capital F is increasing here, right? So here it is positive, there negative, and we can find a neighborhood here. Too much maybe? No, it's okay. So this is neighborhood, here it is, that is k delta x naught. So here it is one-dimensional, but the picture is two-dimensional, right? And in general, we need to have n plus 1 variables. So here, this is in general n-dimensional neighborhood. N-dimensional neighborhood of x naught, right? And what happens? So look, for arbitrary x here, if we fix that variable, right, y is fixed here, x varies, right? We have continuous function. If it is positive here, then it is positive in the neighborhood. That is precisely the neighborhood where capital F is positive. And here it should be negative. So F is positive here, there F is negative. And then what happens? Look, now for arbitrary x, look, what happens then? Capital F, so if I fix x, now, once again, I change roles. Fix x now, but arbitrary in a neighborhood, right? X is fixed, y varies. So it means we go along this vertical line, right? So here it is negative, there it is positive. And partial derivative with respect to y is positive still, right? So once again, now, for arbitrary x in our fixed neighborhood of x naught, f of x, y is an increasing function of y on y naught minus epsilon, y naught plus epsilon, such that capital F of y naught minus epsilon is negative, capital F of x, capital F of x, y naught plus epsilon is positive. So that is increasing, and also it is differentiable, right? But in fact here I don't need differentiability. I need only continuity, in fact, right? And you can find even weaker suppositions for implicit function theorem, namely, you see that in fact what is necessary, look, when we used the partial derivative, we used partial derivative just to find that the function is increasing. If we can guarantee that our function is increasing for arbitrary fixed x, right, then it's enough for us. Continuity plus monotonicity. That's all what we need. But I don't want to go in such weaker formulations. Okay. So from continuity and Bolzano-Cauchy theorem, there exists unique x, there exists unique y equals to, which is by definition f of x, such that f of x y equals to 0 is equivalent to y equals to f of x. So why it is unique? Because we have strictly increasing function, right? Partial derivative is positive. So such a point x is unique, such a point y, is unique, such a point y is unique, and once we choose this uniquely defined point, so what it means? For arbitrary x, we found unique in unique way y. So for arbitrary x there exists y, it means we constructed a function, right? That is by definition f of x. And we solved, right, the equation. Moreover, again, by construction, y equals to f of x is continuous at x naught. Why it is continuous? Because remember what means continuous. For arbitrary epsilon, we should find delta such that when x is sufficiently close, then y's are also sufficiently close. But you see, we did it from the beginning, right? Because we choose arbitrary epsilon. Of course, for different epsilons, the function will be the same, right? Because axis will be on the same, at least the intersection will be for the same, right? So it means the same function. So it means that by the definition, we have continuity at the point x naught. Moreover, you see, so what were suppositions? Partial derivative is not 0, and so on, right? But if I'll consider instead of our point another point of this, then all conditions are satisfied, right? Because function is continuous, differentiable, partial derivative is continuous, non-zero, and so on, right? So it means that we can consider not only function x naught, y naught, but also arbitrary function, arbitrary point such that f should be 0, right? At that point. And you see that we can do it, okay. X, y, x is arbitrary here, right? Y is obtained, so for arbitrary point which satisfies this equation, we can find that function, and it is continuous also at that point. So instead of the point x naught, y naught, we can consider arbitrary point x, y such that f is 0. So, okay, let's have a break. Yeah. So, by the same reason, to prove the last part of our assertion, so you see, we proved everything up to the very last, right? So, uniquely defined function, we constructed it. Not explicitly, of course, but explaining how to do it, right? Now, the last assertion about differentiability. Differentiability in our neighborhood, right? But once again, because of, you see, if we will prove it just differentiability at the point x naught itself, right? Then what we can do? For arbitrary point x where we can solve our equation, right? What we do? We, and you see, in fact, we know that we can solve. I proved it, right? Because, I mean, from the beginning, you see, we had just one point where capital F is 0. But as we saw from the proof, here, always we can find a point where capital F is 0, right? For arbitrary x here, there exists a point where capital F is 0, for sure. And we didn't suppose it, right? But what it means also, that once we can do it, so it means for arbitrary x in our neighborhood, we can find such a y, and after that, for that point xy, what we can do? We can think about that point instead of x naught, y naught, right? Because everything is satisfied. Once again, f of x, y is 0, partial derivative is not 0, continuity, differentiability, everything in a neighborhood, right? Maybe other neighborhood, but doesn't matter. Smaller neighborhood, doesn't matter. Because in a neighborhood, everything is satisfied. So it means that to prove the last assertion, it is sufficient to do it at the point x naught only. So we'll prove differentiability only at that point. So instead of x, just x naught. It's enough. Okay. Now, so capital F is differentiable at x naught, y naught. What it means? It means that we can write an increment of our function, which is capital F x naught delta x, y naught plus delta y, minus capital F x naught y naught. So in general, what we can do, we can write sum k from 1 up to n partial derivative of f with respect to xk at our point times delta xk plus alpha of delta x vector delta y, where alpha of delta x delta y over length of this vector tends to 0 as this length tends to 0. Look, y naught plus delta y, what is it? That is y naught, right? Y naught plus delta y is that one, right? Y naught plus delta y is the value of f, right? But we know that if we have a value at this point, right, then capital F is 0, right? So that is 0, and that is 0 as well. So that is in fact 0 for arbitrary delta x sufficiently small. So if I put delta y like that, then for all sufficiently small delta x, that is 0. Right? Okay. Now, put delta alpha, not y delta, just alpha j of delta x delta y, but in fact y of delta y. Remember, delta y also depends on delta x somehow, so I may write like that. Alpha j of delta x, by the definition, that is what? Alpha of delta x delta y over the length of this vector times delta xj over the same length. Yeah, remember once again, delta y here is fixed, right? Not fixed, but I mean, once you have delta x, delta y is determinate. So delta y depends on delta x. And yeah, I'm sorry, I forget about very important thing. So the most important thing I forget, because capital F has n+1 variables, right? I wrote n variables. I forget about n+1. So here I should insert also, okay, let me write it here, plus partial derivative of f with respect to y at x naught, y naught times delta y plus alpha of delta x delta y, right? Yeah, this should be correct. Sorry, yeah, I forget. Okay, so now which letter? Okay, let me write beta of delta x to be the related, so once again alpha of delta x delta y over the length delta y times analogously delta y over this length. Okay, let me recall with delta y equals to f x naught plus delta x minus f at x naught, right? That is everywhere here. That is why I omit delta y. Okay. Then, as we know, if delta xj tends to 0, j from 1 up to n, then what happens? First of all, continuity of f guarantees that delta y tends to 0, right? F is continuous, so if the vector tends to 0, then delta y tends to 0, right? Also, from both follows, what follows? Look. So now you see, this vector tends to 0, delta y tends to 0. By the definition, this ratio tends to 0, right? So first term tends to 0 and second term is less or equal to 1 in modulus, because module of one component less or equal than the length of the vector, right? So we have product of infinitely small times bounded. Tends to 0, bounded. The product is infinitely small. Tends to 0, right? So we deduce that both alpha j and beta tend to 0. That's very important. And after that, okay, let me, for a while, let me erase two blackboards. But here, I'll keep the last assertion, which we are proving now, right? Okay. So let me how to rewrite it better. Okay. So yeah. So you see, I'll divide this equality by square of this length. Right? 0 equals to that one divided by square, right? And then look. Then our equality can be rewritten as follows. 0 equals to the sum k from 1 up to n maybe it's better to mention it here. Look, if I'll consider such a sum, alpha j squared plus beta squared, then look, what is it? Look, so I have alpha squared, right? That is common multiplier, right? Then yeah. Just a minute. Okay, let me write what I want, and then I'll understand how to write it correctly. So at x naught, y naught plus alpha k of delta x, yeah, plus partial derivative f with respect to y, x naught, y naught plus beta of delta x. That is what. So the sum of alpha j. Yeah, what I forget, very important thing, delta xk, yeah, and here times delta y. Yeah, not squares, yeah, you see, if we consider such a product, delta xj plus beta times delta y. So what if we'll consider this expression? What happens? Look, oh, there is a question. We can attend the class in person. Oops. It seems so. I don't know who is responsible for that restriction. Okay, so you see, yeah, but it's important question. I should to clarify it, by the way. Yeah. Look, so what we do? We have alpha j, right? Multiplied by delta xj. And what we have? We have delta xj squared, right? Multiplied by delta y, we have delta y squared here, right? If we add all of them, then you see everything else is a common multiplier, right? But sum of squares of delta xj and delta y is precisely square of this length. Because what is square of delta x, delta y? Is sum of squares of components, right? Right. So you see, we have common multiplier times that one. So we cancel that. What remains? Only alpha. So that is precisely alpha of delta x, delta y. That's important. So you see now what is written here. Alpha k times delta xk, sum of them, plus beta times delta y, right? That is precisely our function alpha. That is why this is precisely the same as I had here. Roughly speaking, I distributed alpha among each of those terms, right? With the help of those functions, right? Okay, now look, we know this tends to 0, right? And that is not 0, we know. So it means this term is not 0 in a neighborhood, right? In, let's say, k delta x naught. Or in a smaller neighborhood, maybe. In a subset of that. Doesn't matter. For sufficiently small delta x, it is not 0, right? Maybe. I'll put here delta tilde. Maybe smaller. I cannot guarantee that it is not 0. But, look, if this is not 0, then what I can do? I can divide by this expression. So, what follows? Delta y equals to the sum k from 1 up to n minus, right, appears, and then this ratio. Over times delta xk. And now I can rewrite this expression as, let me write it like that. Sum k from 1 up to n, partial derivative, okay, let me put minus inside, partial derivative of xk over partial derivative of y, both are at that point, plus something gamma of delta x times delta xk. So look, what we know about alpha k beta. Both tend to 0, right? Tend to 0, tend to 0. So it means this ratio tend to the ratio of those partial derivatives, right? So I can write it like that. This ratio of partial derivatives plus something which tend to 0, right? Something which tend to 0. That something I'll denote by gamma. And after that, I can write as follows. Sum k from 1 up to n minus partial derivative of, partial derivative of f with respect to xk at x naught, y naught, over partial derivative of f with respect to y, x naught, y naught, yeah, times delta xk plus everything else. Okay, let me write it here. Gamma of delta x times delta x, gamma k, let it be here, gamma k. Index should be included also, right? For every term, it's its own function. So now you see, look, what happens? What is about this term? If we divide by the norm of this vector, then what happens? This ratio, delta xk divided by this vector, is bounded, right? And this tends to 0. So it means if we divide this sum by this vector, this quantity tends to 0, right? But remember, what is delta y? Delta y is f x naught plus delta x minus f at x naught. So the increment of our function is represented as a sum of linear terms, right, plus something which tends to 0 after division by delta x. That is precisely the definition of differentiability of f, little f, right? So what we obtained proves the differentiability. Differentiability is proved at x naught, right? And as I said, it's sufficient for us to prove just differentiability at the point x naught. And also partial derivatives are computed, because coefficients in delta xk are partial derivatives, right, of the function f. So the proof is completed. The proof is completed. Oops. Okay. So in Russian, when I gave lectures, not here, before in Saratov, I usually called this theorem the simplest implicit function theorem. After that, second. Okay, so it was simplest. So, but it seems I have, of course, I have no time to prove. Maybe I'll be able to formulate it. Yeah, I think I can do it. But before, look, implicit function theorems, what was written, right? So you saw also questions. There was a question why y has no vector, right? Now it will appear. But look, what means we have many y. It means how we can solve the equation to find a vector. We have to solve not one equation, but a system of equations, right? So that is what we'll consider. So now, but before to do it, I need some definitions. So now we'll consider a system of equations. Okay, let it be like that. So we have a system of m equations with n plus m variables. You see, n variables x, m variables y's. And we want to solve this system of equations with respect to the last m variables. And look, that is a generalization of what we had before, right? Before we had one variable y and we had one equation. So before we considered the case m equals to 1. So it means what we did was m equals to 1 for induction. Right? That was m equals 1 to induction. The first step of the induction. Okay. Now, before we had partial derivative of our one function with respect to the last variable, right? So now we have many functions and of course many partial derivatives. And what to do? It turned out that the replacement of a partial derivative will be so-called Jacobian determinant. So Jacobian determinant of, okay, maybe I'll denote just f1 so on fm with respect to y1 so ym is by definition the following determinant. Did you use this notation in linear algebra? Determinant, just one vertical line, right? So df1 over dy1, so on, df1 over dym, so on, fm dy1, dfm over ym. Where all partial derivatives are computed at the same point. So, and that is precisely so, you see, Jacobian determinant depends on values of all those partial derivatives at a point, right? So Jacobian determinant at a point, in fact, right? I didn't indicate the point here, but I should, of course, in general. So now, but I'm afraid 5 minutes is not sufficient even to formulate. No, it is not sufficient. And okay, maybe before to go further, let me once again to revise the implicit function theorem. So let me recall how we solved it. So we had equation, right? And we solve it. So it means we find a function such that this is identity, right? Now there is very simple way to understand how to find derivative of such a function, right? So now I forget about vector, just 1, 1. How to find derivative? You differentiate. This is identity, right? So we can differentiate it. And we differentiate it using chain rule for functions of several derivatives. So full derivative is equal to partial derivative of with respect to x plus partial derivative with respect to y, second variable, times f prime. And that is 0, right? Because we differentiate identical 0. So what is about f prime? Minus df over dx over df over dy. If you have many variables here, the situation is completely similar, right? But instead of full derivative here, I mean usual derivative, you should consider partial with respect to a variable x. So that is how we obtain the formula. We just substitute and differentiate. Similarly, we can proceed here. We solve this equation, so we obtain m functions of n variables. M functions, every y is a function of n variables, right? If we substitute, we have identities. We have m identities. We differentiate them with respect to every variable, right? And after that, here we had one equation. Now we obtain several system of equations, right? Linear equations, that's important, linear equations. And determinant of that system is that one. That is why this Jacobian is very important. Determinant of that system is that one. So if it is not 0, then we can solve it. If determinant of linear system of equation is not 0, then you can solve the system of linear equation, right? Linear equations, right? And that is the way how you will find partial derivatives and why you can be sure that the function is differentiable. That is how determinants appear here, right? Okay, but I have no time to start to formulate the theorem, so let's stop here.